Well, welcome, Math 347 fans. Part 1 on an introduction to Laplace transforms. In this video, we'll define the Laplace transform as an integral transform, start building up our intuition, sort of a little bit of a library of how to take transforms. We'll also talk about the inverse transform and illustrate some strategies and methods for finding those inverse transforms. Part 2, we'll look at some properties of the transform. Okay, so overall, the goal of this chapter is to continue to solve differential equations. So we're not introducing a new differential equation, just a new method for solving differential equations. However, in particular, we're going to be trying to solve differential equations where the forcing term f is possibly discontinuous. Okay, so we'll see later how Laplace transforms are super powerful tool in that respect. Okay, so let's start off with the definition of a transform. Here is the definition of an integral transform. The expression, the integral from a to b, k of s and t times f of t dt is called an integral transform. A little bit of terminology. This is typically the transform of some function f, where the function k is a kernel. Even if you haven't seen a function of more than one variable in other classes before, you can sort of think of this kernel k as some function that has s's and t's in it. And in this integral, we'll go ahead and just treat the s like it's a constant. So this is just a calculus 1 integral in the variable t, where we think of s as a constant. As you might imagine, this will yield a function of s. Okay, so as an example of an integral transform, let's take the kernel to be 2st, and let's take f of t to be t, and let's go ahead and compute the transform of this function f with the kernel k. Okay, so I'm going to call this capital F, the transform. Okay, so in this case, again, we're just thinking of s as a constant in this integral with respect to t, so it can be pulled outside. This is just a calc 1 integral now in t, and when you work it out, of course, you get this function of s that in this case is 14s over 3. So as you might imagine, for the same kernel, different functions have different transforms, and even if you chose a different kernel, of course, the same function would have a different transform. Okay, so the Laplace transform is such an integral transform too. The Laplace transform is the transform of a function that's defined for t greater than or equal to 0, and it's an integral transform where the integral is from 0 to infinity, the kernel e to the minus st, and we'll integrate against x of t dt. So as you can imagine, this is going to give us a function of s. Well, maybe, right? So one of the things we know about this integral being an improper integral is that it may or may not converge. In general, in this class, we're going to be interested in integrals that converge. But nevertheless, we'll go ahead and use our Calc 2 knowledge to address this integral as the limit of a finite integral. Okay, so we'll write our transform of the function f, or here it's x. I've expressed it below as f as the limit as b goes to infinity of the integral from 0 to b of our kernel, e to the minus st times f of t dt. And again, we'll be interested in such integrals that converge. Okay, a little bit of notation. Provided that the integral converges, the result is a function of s, and the domain of that function typically depends on s, where s is defined such that the integral converges. And we typically use capital letters to denote the transform, so the Laplace transform of little x would be capital X, the Laplace transform of little f would be capital F, and similarly for little g and big G, and so on. Okay, here is our very first Laplace transform. Let's go ahead and have a look at the Laplace transform of the function 1. So by definition, the Laplace transform of 1 is the integral from 0 to infinity of, again, our kernel, which is e to the minus st, times the function 1 dt. So again, I'll go ahead and write this as the limit as b goes to infinity of a definite integral from 0 to b of e to the minus st. We can integrate that quickly as minus 1 over s e to the minus st and take the limit as b goes to infinity. And you can imagine that this limit is finite just so long as s is a positive number. Okay, so in that case, when s is a positive number, the e to the minus sb goes to 0 as b goes to infinity, and we end up with 1 over s. So we say that the Laplace transform of 1 is 1 over s, and its domain is s greater than 0. Okay, our very first Laplace transform. Another Laplace transform, let's go ahead and have a look at the function e to the 3t. So let's find the Laplace transform of e to the 3t. So similarly, we integrate e to the 3t against our kernel e to the minus st from 0 to infinity, express that improper integral as the limit of a definite integral from 0 to b. Go ahead and take the integral, and we see there that our limit exists. That is, this term goes to 0 just so long as s is bigger than 3. So in this case, the Laplace transform turns out to be 1 over s minus 3, just so long as s is greater than 3. Now you can imagine there's nothing really special about the 3 in that example, so we can have a look at the Laplace transform of e to the kt, similarly as the integral of e to the kt against our kernel e to the minus st from 0 to infinity. Similarly, this e to the minus s minus kb goes to 0 just so long as b as k is as s minus k is positive, so as long as s is greater than k. So the Laplace transform of e to the kt is 1 over s minus k with domain s greater than k. Let's have a look at another Laplace transform. Here's the Laplace transform of the function t. So by definition, the Laplace transform of the function t is the integral of t against our kernel e to the minus st from 0 to infinity. We rewrite that as proper integral, and the limit as b goes to infinity. And you can imagine that for this particular integral, you'll need to go ahead and use integration by parts, right? So find the antiderivative of t e to the minus st with parts. When you do that, obtain sort of a complicated expression for the value of the definite integral on the interval from 0 to b. Now, one thing that happens is that the second term is going to go to 0 quickly, right? This term goes to 0 quickly as long as s is greater than 0. Sorry, as long as s is greater than 0. And this term, as it turns out, goes to 0 too, as b goes to infinity, but you need a L'Hopital's rule technically to show that. So you might remember L'Hopital's rule from Calculus 2. L'Hopital's rule tells us that the value of this limit is 1 over s squared, just so long, again, as s is a positive number. So here's another new transform, the transform of the function t. The transform of the function t is 1 over s squared. Again, its domain is s greater than 0. It's worth mentioning that the Laplace transform is a linear operator. It's linear in the same sense as it was linear before, namely that the transform of a sum is the sum of the transforms, and the transform of a scalar multiple of a function is the scalar multiple of the transform, again, assuming that the integrals converge. So we can see this quickly just by applying the definition, right? The transform of f plus g is an integral of f plus g against the kernel, which we know the integral of a sum is the sum of the integrals just so long as the integrals converge, which is the Laplace transform of f plus the Laplace transform of g. And it works similarly for the Laplace transform of a scalar multiple as well. The Laplace transform of alpha f is alpha f times the integral times the kernel integrated from 0 to infinity. And of course, if the integral converges, that alpha can be factored out front, giving us alpha times the Laplace transform of f. So linearity is a pretty huge tool for Laplace transforms, as it's been earlier in this course. For instance, we can find the Laplace transform of this function 2t plus 7e to the 3t using linearity and the transforms we already know. right? So the transform of the sum is the sum of the transforms. That's what this first line says. And the second line says that the transform of a constant multiple of a function is a constant times the transform of the function, right? So that's linearity also. This gives us that the transform, since the transform of t is 1 over s squared and the transform of e to the 3t is 1 over s minus 3, the transform of 2t plus 7 e to the 3t is 2 over s squared plus 7 over s minus 3. And I'm not going to belabor the domain too much longer, but I will say that we'll take the domain to be the intersection of the two domains, which in this case is s greater than 3. Turns out linearity combined with Euler's identity is a convenient way to identify the Laplace transform of the sine and the cosine. So I'll go ahead and work through the Laplace transform here of cosine. By definition, the Laplace transform of the cosine can be written as the Laplace transform of this combination of exponentials, right? So use linearity twice here to break down the sum and the product. And then here, even with the complex argument, we can still write the transform of e to the ikt is 1 over s minus ik, and the transform of e to the minus ikt is 1 over s plus ik. These two terms combine pretty quickly just using the conjugate, right? So multiply both terms by the conjugate, and that conjugate ends up giving you the denominator of s squared plus k squared, and the transform of the cosine function is given as s over s squared plus k squared. It turns out that this little delve into complex arithmetic is a much easier route to identifying the transform. Otherwise, we would have to integrate cosine against an exponential, and of course, integrating by parts twice, reproducing the original integral, and then finally taking the limit as t goes to infinity, actually using the squeeze rule to show that limit exists. So a little bit of complex arithmetic makes our life a little bit easier in this case. We can use our new transform now in linearity to find the transform of 2 plus 3 cosine 5t. So here I've done both steps of linearity at once, right? The transform of the sum and then pulling out those constant multiples. Of course, the transform of 1 is just 1 over s, and the transform of cosine 5t is s over s squared plus 25, giving us the transform of the desired function. The transform of the sine function turns out to be similar. That's a homework problem, so I'll let you go ahead and work through that in your homework. Okay, so here's sort of a list of some transforms, some of which we've found, and actually some of which we haven't yet, but we will soon. So the transform of 1, we found the transform of t. It turns out that transforms of t to powers follow a nice pattern. The transform of the exponential and the sine and the cosine. And it turns out that the transforms of the hyperbolic sine and hyperbolic cosine follow similar patterns to sine and cosine, just with the minus sign instead. So sometimes those are useful to use too. Okay. All right, so let's go ahead and talk now about the inverse transform. So it turns out there's an integral formulation for the inverse transform as well, but that integral formulation is sort of beyond the scope of this course. So instead, we'll define the inverse transform of a function f of s as little f, just so long as we can transform f, little f, and get back capital F. So if the forward transform of little f is big F, then the inverse transform of big F is little f. And as you might imagine, linearity comes in handy too, but the main tools for identifying the inverse transform end up being also multiplying and dividing by the same amount, adding and subtracting by the same amount, and a couple tricks we've seen previously, including completing the square and a partial fraction decomposition. So we'll see those throughout as we go through more of these inverse transforms. Okay, so here's an example. Let's find the inverse transform of 1 over s. So you stare at your chart and you stare at the function you want to invert, and you stare at your chart and you stare at the function you want to invert, and you realize that the forward transform of 1 is 1 over s. Therefore, the inverse transform of 1 over s is 1. Okay, so there's your very first inverse transform. A second example, let's go ahead and have a look at the inverse transform of 1 over s to the fourth. Okay, so 1 over s to the fourth looks somewhat like the transform of t cubed, except we're off by a factor in the numerator. Okay, so here's our first manipulation, multiplying and dividing by the same amount. I'll express 1 over s to the fourth as 1 over 3 factorial times 3 factorial over s to the fourth. And again, I'm manipulating this way in order to identify the transform of t to the n, where n is equal to 3. So now linearity comes in handy here. The inverse transform of 1 over s to the fourth is the same as the inverse transform where we've multiplied and divided by the same amount, 3 factorial. Okay, of course that 1 over 3 factorial can be factored out front, giving us the inverse transform of something we recognize, which is t cubed, so that the inverse transform of 1 over s to the fourth turns out to be 1 over 6 t cubed. Okay. This multiplying and dividing trick is pretty handy, and it comes up pretty frequently. Here's another example. Let's go ahead and have a look at the inverse transform. I've got a small typo here. This should be the inverse transform of 1 over 2s plus 1. So this should be the inverse transform of 1 over 2s plus 1. Sorry about that. Okay, so this form doesn't look a whole lot like anything in our chart, but it looks most like the transform of an exponential function, right, with a linear factor of s in the denominator. Okay, so here we'll go ahead and manipulate our transform, factoring out a 2 from the denominator. So here we factor out a 2 from s and from 1 to write this as 2 times the quantity s plus 1/2. So you can think of this as s minus a minus 1/2. And again, linearity gives us the inverse transform here. The inverse transform is 1/2 times the inverse transform of 1 over s plus 2, or s minus a minus 1/2, which is 1/2 times e to the minus t over 2. Another inverse transform using that multiplying and dividing trick again. Here's the inverse transform, another typo here, sorry about that, of 1 over s squared plus 5. So stare at 1 over s squared plus 5 in our chart and s squared plus 5 in our chart, and notice that it looks most like the transform of a sine function, right, with a constant over s squared plus k squared. Okay, so we can manipulate this to look exactly like the transform of a sine function times a constant multiplying and dividing by the square root of 5, just so long as we recognize the square root of 5 as being k in this example. Okay, so multiplying and dividing by the square root of 5 and using linearity here, the inverse transform of 1 over s squared plus 5 is 1 over the square root of 5 times the sine of square root 5t. Okay. Another example, using a new method. So here is the inverse transform of something that looks quadratic in the denominator. Now I'll remind you that we can use a partial fraction decomposition to take this rational function apart into 2 parts. Okay, so I won't go through the details of that. This is something we did at the very beginning of the class, but this is something that comes from Calc 2, so it's something we have to know how to do here too. Okay, so partial fraction decomposition gives us that 1 over s minus 4 times s plus 6 is 1 over s minus 4 times 1/10 minus 1/10 times 1 over x plus 6. And now, lo and behold, it looks like 2 transforms of exponentials that we have here. Okay, so in this case, the inverse transform of the rational function is the inverse transform of 1/10 1 over s minus 4 minus 1/10 1 over s plus 6, which, using linearity and the transform of e to the kt, is this combination of exponential functions that we see here. Okay. Another partial fraction decomposition example, a more complicated one. Here is the inverse transform of 2s over the quantity s plus 1 times s squared plus 4. Okay, so again, a partial fraction decomposition in this case. tells us how to take apart this rational function into several parts. There should be a 2s here, not a 1. Sorry about that typo. So a 2s in the numerator comes apart, and we obtain this form for the partial fraction decomposition. Okay, in this case, we can sort of recognize the first term as the transform of an exponential. The second term looks like the transform of a cosine, and the third term looks somewhat like the transform of a sine. So that third term requires a little bit of manipulation too. In this case, we'll take our 8 apart and leave a 2 in the numerator with a 4 out front to get us the correct constant k for our sine term. So the inverse transform here ends up being a combination of an exponential, a cosine, and a sine. Okay, we'll go ahead and stop this video here and pick up with our basic properties in our next video. Thanks for watching. Hope you enjoyed the video. So long for now.